Now we are ready to talk about the singular value decomposition. The singular value decomposition is defined for any matrix. So the matrix A can be a rectangular matrix of size m by n, and it is a generalization of the diagonalization for square matrices, which, as noted, doesn't always exist. While the singular value decomposition exists for every single rectangular matrix A, including obviously the square ones. In a similar ways to a diagonalization of a matrix, the singular value decomposition is not unique because one could rearrange columns. But if you focus just on eigenvectors or singular vectors in this case and the corresponding singular values, then we do have uniqueness up to some restrictions. So to summarize, A is an m by n matrix. Let's say A is of rank R. We know that the rank has to be is bounded by m and n. These matrices U, so U and V are orthogonal matrices. Remember that this means that U and V have to be square matrices as well, because we said we will reserve the word orthogonal matrices only for square matrices. And sigma is a diagonal matrix that contains the singular values of A. Now, let's see what kind of sizes these matrices would have to be for this diagonalization or the singular value decomposition to make sense. Well, sigma and A will have the same size. We want sigma to represent some kind of diagonal form. So this diagonal, of course, for a rectangular matrix, you kind of have to focus on what does diagonal mean for a rectangular matrix, and we'll talk about that. I will give you, through examples, you'll see exactly what I mean. So because we want sigma to be this diagonal representation of A, we want sigma to be the same size as A. So sigma is also m by n. And sigma also has rank R. So the rank of sigma also is R. And this has to happen because the orthogonal matrices here, you see, these are invertible orthogonal things. They do not change the rank of sigma. They preserve the rank of sigma. Orthogonal transformations always, or invertible transformations, preserve rank. So the rank of A and the rank of sigma have to be the same. So this is a rank R matrix of size m by n, and then just by, so that multiplication would make sense, so if this here is m by n and this is m by n, now that forces U to be something by m, and since it is a square matrix, it must be m by m, and then V must be n by n. So this tells us a little bit about where these matrices act, so on which subspace of A. So we have, I'll just complete here. U is m by m, and V is n by n. Okay. I know I put a lot of information here without explaining where this decomposition comes from or to even prove that it exists. But for the time being, assume it exists. Assume we can find such a decomposition for the matrix A. And let's explore to see where we could find the matrices U, sigma, and V transpose. So it's almost like, imagine I had a dream that A would split into a U sigma V transpose, then what? And by starting sort of from the result, we will show that the result exists. Well, there are two matrices. So remember, in the previous video on symmetric matrices, I said symmetric matrices will be the key to us finding the singular value decomposition. The reason symmetric matrices are so important is that they always can be diagonalized. Their eigenvalues are always real numbers, and their eigenvectors can be chosen to be orthonormal. So then, if I have a rectangular matrix A, how do I, what are the symmetric matrices that I can look at that relate to A? Well, every A generates two symmetric matrices. It generates A transpose and A transpose A. A transpose and A transpose A are not the same matrices. Sometimes even their sizes are not the same. In fact, whenever A is rectangular but not square, A transpose and A transpose A will have different sizes. Further, so these matrices, these are symmetric, which of course also means square. And they have one more property, which is called, they are positive semi-definite. We can talk a lot about what that means and how to discover whether matrices are like that. But for us, what positive semi-definite means is that all eigenvalues are bigger than or equal to 0. Okay, so they have non-negative eigenvalues. And when this is the definition of positive semi-definite, all eigenvalues are non-negative. But there is quite to be said about how to decide whether a matrix is positive semi-definite or not. I will not go into the proof as to why these matrices are positive semi-definite, but I will stick to the fact that A transpose and then A transpose A, they are symmetric matrices. That is obvious, can easily be confirmed. Just take the transpose. And we will know that their eigenvalues are always bigger than or equal to 0. In fact, there is one more property that these two matrices share, and that is that the non-zero values, this is a very important property, the non-zero eigenvalues of A transpose are also the non-zero eigenvalues of A transpose A. I have to highlight this non-zero part, and the reason for that is that, let's say on an example, if A is, say, 3 by 2, okay, 3 rows, 2 columns, then A transpose will be 3 by 3, whereas A transpose A will be 2 by 2. Now, a 2 by 2 matrix has 2 eigenvalues, whereas a 3 by 3 matrix has 3 eigenvalues. The key here is that A transpose will definitely have to have one eigenvalue equal to 0, because A transpose A and A transpose share the same non-zero eigenvalues, or the same positive eigenvalues, and the rest are zeros. So we know for a fact that A transpose will have at least one, possibly more, will have at least one eigenvalue equal to 0. Because, I repeat, these two matrices have to have the same non-zero eigenvalues. So this is something very powerful. Same eigenvalues here and here. Okay. What do we do with that? Again, A equals U sigma V transpose. So under the assumption that this is A, what will then be A transpose, for example? Well, let's write the what we get from this singular value decomposition for the matrix A. We get U sigma V transpose times U sigma V transpose transposed, right? So here we're going to get U, well, I guess I don't need brackets, U sigma V transpose, and then remember we apply transposition to each matrix but write the result in the opposite order. So I would have V transpose transpose, but that's just V. Then I have sigma transpose, which is not the same as sigma, even though this is a diagonal matrix, because sigma is assumed to be rectangular. So the sizes don't match. And then I have U transpose. So what do I have here? V transpose V, because V is an orthogonal matrix, V transpose V is just the identity. So what I have, so this is the identity matrix. So A transpose is essentially U sigma transpose U transpose. Now sigma transpose is actually a diagonal matrix. This over here is a diagonal matrix. We could call it lambda if you like. Okay, so we see here that A transpose equals U lambda U transpose. Now the question is, can this happen? Would it be possible that any time that for any matrix A, given a rectangular matrix A, is it true that there is always a matrix U, an orthogonal matrix U, such that A transpose equals this diagonalization? The answer is yes, because A transpose is in fact a symmetric matrix. So the symmetry of A transpose guarantees that U exists. And here, in fact, when you multiply sigma by sigma transpose, you get squares. So the singular values that go into these matrices get squared here. So this is actually proving that lambda will have to have positive numbers. So the eigenvalues of A transpose have to be, well, at least non-negative. They could be zeros or positive numbers. Now, by knowing, there is a way, of course, to prove that A transpose is a positive semi-definite matrix, which proves that this matrix lambda will have numbers bigger than or equal to 0. So this is what we need to guarantee, and we can always find such a matrix U because this matrix is symmetric. So we know that this decomposition works, or this factorization works. So we know that we can always find U, and this is exactly the process to find U. Find the diagonalization of A transpose, and you have found yourself U. You have found yourself lambda, which in turn will define sigma. So actually, A transpose defines the matrices U and sigma. So then where is V transpose? Or where is V coming from? Well, we can try now A transpose A. Okay, what's A transpose A? Well, now the transpose will be applied to U sigma V transpose on the left-hand side. We multiply by U sigma V transpose. And then we get V sigma transpose U transpose, U sigma V transpose. Now U transpose U is the identity. Now the two identities are of different sizes, but they're still the identity. And so here we get V sigma transpose sigma V transpose. Now, I want to call this sigma transpose sigma a lambda too, but they would not be the same lambdas. This is again a diagonal matrix, but it's not the same lambda. It has the same non-zero numbers, but it is not the same size. So there may be more zeros or fewer zeros. So sort of like lambda, but possibly smaller or bigger depending on the size of A. The key here is, maybe we call this matrix M for now. Okay, it will consist of mu's, so that I can say A transpose A equals V M V transpose. Okay, and because A transpose A is a symmetric matrix, I know that I can find a matrix of eigenvectors which is orthogonal, because the eigenvectors of a symmetric matrix can be chosen to be orthogonal. Using the fact that A transpose A is a positive semi-definite matrix, I know that the eigenvalues corresponding to the vectors in V are actually going to be 0 or greater than or equal to 0. So there will be positive or non-negative, sorry. So we see that it is possible to find the matrix U, the matrix sigma, and the matrix V from A transpose and A transpose A. They can always be computed for any rectangular matrix, and that is indeed the procedure that we're going to use to compute the singular value decomposition. Now, to describe the procedure for it, so I already gave you sort of a hint, but the issue is that when you look at the singular value decomposition, U sigma V transpose, it's not unique. There could be different U's and different V's, and the sigmas, well, the sigma values will be the same, but they can be rearranged, right? So that's an issue. And so we don't really go to find all the eigenvectors of U and all the eigenvectors of V. We actually don't go looking for A transpose and A transpose A. We use one or the other, not both. Now here, if I multiply both sides by V, I'm going to get A times V equals U times sigma. This is in fact the equation that is more useful. Why is that the case? Well, I can write n equations. Well, will it be n? Let's see. So A is m by n. So now V is n by n. And U is m by m. I need to keep that in mind. I want to know how many columns I have in V, how many columns I have in U. So I have n many products A times V, okay, in the columns of V. So let me write that as a matrix. AV is A times, so V is an orthogonal matrix with columns V1, V2, VR, and then VR plus 1, all the way to Vn. Why did I put VR there? That's very important because I know that the matrix A is of rank R, right? So rank of A is R. But the matrix V has n columns. The matrix V has columns for every, the columns of the matrix V give us a basis for the space Rn. So here is Rn. Okay. Well, I want to draw the picture. So first let me give you Rm. The picture that depicts the four fundamental subspaces of the matrix A. And I feel like this will be maybe a little difficult to see. So there. So if you remember, here we have the row space. So C of A transpose. Here we have the null space. And then, oh no, that's an N. My apology. That's Rn. And then we have Rn here. Rn. This is the column space of A. And then its orthogonal complement, the left null space. So remember, the row space of a matrix is the orthogonal complement of the null space. So if you take any vector from the row space, it's going to be orthogonal to any vector from the null space. So these two spaces are orthogonal. So what's happening with this matrix V? We said that if we have n linearly independent vectors from Rn, and that's exactly what we have here in the matrix V, that gives us a basis for Rn. These vectors are orthonormal, right? They give us an orthonormal basis for Rn. Therefore, exactly R many of them have to be in the row space, and the remaining n minus R many have to be in the null space. So if we decide to order these vectors such that the first R many of them correspond to non-zero singular values, and the remaining ones correspond to zero eigenvalue, singular values, then what we have is a basis for the row space and a basis for the null space of the matrix A. So let me write that. This over here will be a basis for the row space. And then this will have to be a basis for the null space. Why is that? Does that have to be a basis for the null space? Because the row space and the null space are orthogonal complements, because this space is orthogonal to this space. They're orthogonal complements of each other because we have an orthonormal basis here. We have an orthonormal basis for Rn, where we have chosen the first R vectors from the row space and the remaining n minus R vectors from the null space. Okay, so we have this. Now I can carry out the multiplication A times V, one column at a time. So when I look at AV equals U sigma, what do I get? Well, I have A times V1. It needs to be the first column of the product U sigma, but that is simply sigma 1 U1. And all the way to AVR, I have sigma R U R. So if R is of rank R, if A is of rank R, that tells me that A has R non-zero singular values. So there have to be R non-zero singular values. Remember, the number of eigenvalues has to do with the rank, has to do with the number of non-zero pivots, the trace, the determinant, they all come into play. So you see the equation AV equals U sigma. What happens with the rest? What happens with all the others, all the other V's? So AVR plus 1, because VR plus 1 is in the null space of A, is just 0. And all the way to AVN, we get 0. So you see, when you multiply the matrix A times V, you don't get everything. You get the first R vectors of the matrix U, but they have to correspond to these V's. You see, if I switch places here, right, if I rearrange these V's, I'm still going to have a basis for the row space, but they will correspond to different vectors U. These vectors U continue to be singular eigenvectors for A transpose, because the V's we said right over here, the V's are eigenvectors of A transpose A, whereas the U's are eigenvectors of A transpose. But you see, there are the eigenvectors of A transpose A correspond to certain eigenvectors of A transpose. So we have to be careful which eigenvector here is mapped to which eigenvector there. If we find eigenvectors for A transpose A, put them in a matrix V, and do the same thing here. Yes, we will find a U that does this. We will find a V that does this. But this U and this V will not match to give us the singular value decomposition of A. So we have to be careful. We can't go down these independent routes. We have to stick to one of them. Say we find V, and then we will use V to find the corresponding U by using the fundamental theorem of linear algebra and these equations. So you see, what happens now is that AV1 is just a multiple of U1. Well, where is U1? Where the sigma is just a number. So think of this as U1. This is in the column space of A. You see, the vectors that we choose here, the V1 all the way through VR, they get mapped into the column space. And the null space vectors, well, the null space vectors get mapped to 0. But what's important is that the corresponding U's in the matrix U, V1 will get mapped to sigma 1 U1, V2 will get mapped to sigma 2 U2, and VR will get mapped to sigma R VR. I cannot rearrange this. This is fixed. This vector goes here. This vector goes there. I don't just look at the set of vectors, but the specific ones. And then how do I find the remaining U's? Well, for UR plus 1 all the way to UM, they have to be in the left null space. They're all in the left null space of A. So I can just find them there. I just need an orthogonal basis for the left null space of A. So what we see here is that the singular value decomposition actually comes from the bases of the 4 fundamental subspaces of A that are orthonormal, and they're just the right basis. So I could take, you see, some other orthonormal basis for this space, but I will have no guarantee that it will map into an orthonormal basis here. Whereas when we take these singular value or the singular vectors, these particular vectors, the unorthonormal basis here will map into an orthonormal basis there. The rest of the columns get picked by just taking an orthonormal basis for the null space, which will by default be orthogonal to that basis because the spaces are orthogonals. And same here for the left null space. So if I write the whole matrix A as U times sigma times V transpose, I have U here, U1, UR. I need to pay attention to that R. Then I have UR plus 1 to UN. I think I'm making a mistake. So U is M by M. So that's all the way to M. Then I have sigma. Now here's what sigma looks like. So A we said is M by N, right? This is M by N. But A is of rank R. So we look at this submatrix here, R, R, the square upper left corner. And this is where all the non-zero singular values are. Here is sigma 1 all the way to sigma R, and everything else in this matrix is 0. That's it. This matrix has only this square submatrix that contains the singular values. Everything else is 0. So this is the way in which we think of this matrix as diagonal. And then the matrix V, remember this is transposed, so this will be an n by n matrix. This is m by m. That matrix contains V1 transpose as the first row all the way to VR transpose. And then we have VR plus 1 all the way to VN transpose. So a reminder, this part gives us a basis for the column space of A. This part gives us a basis for the left null space. These R vectors give us a basis for the row space. And the remaining n-1 vectors give us a basis for the null space of A. So this singular value decomposition gives us yet another beautiful it lets us see the fundamental theorem of linear algebra in play in these in these matrices. It is the right choice of bases for this diagonalized representation of the matrix A. What are sigma 1 through sigma r? Well, if we focus on this equation here, if I look at the length on both sides, so let me write that. If we have AV1 equals sigma 1 U1, then, so both sides represent a vector, I could take the norms of each side, right? But remember that V1 and U1, these are unit vectors. So actually, I know that their norms are 1. Sigma 1 comes out. I know sigma is a positive number. So I have sigma 1 times the length of U1. The length of U1 is simply 1, so I just get sigma 1. So sigma 1 is the length of the vector A times V1. Sigma 2 will be the length of A times V2, and so on. So we have this beautiful decomposition that sort of brings us to this perfect circle of eigenvalues, eigenvectors tying up to the fundamental theorem of linear algebra. We have the perfect bases for the singular value decomposition. Now, from this picture, we have a generalization of the spectral theorem. Remember, the spectral theorem for symmetric matrices gave us the following. We had C equals Q lambda Q transpose can be written as a sum of rank 1 matrices. So we had lambda 1 Q1 Q1 transpose plus lambda 2 Q2 Q2 transpose all the way to lambda n Qn Qn transpose. Well, we have this generalization from the singular value decomposition that allows us to write A as a sum of R many rank 1 matrices. There have to be R because A is of rank R. So those matrices are given by sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose all the way to sigma R UR VR transpose. Why is this representation important? Where does it get where are the applications of this decomposition? One place where we see applications is image processing. We could also talk about saving memory. So for example, instead of sending this entire decomposition, sending these matrices, sending so many vectors or multiplying them out, you could just send, instead of this matrix, you could send the vector U1 and the vector V1 transpose and the scalar sigma 1 instead of that matrix. And what is important is that the bigger the value of sigma, the more important this matrix is. So if your matrix A represents some image, think of, your computer screen or your tablet or your phone. The screen has a certain number of pixels. And depending on whether you have, say, blue or red or green on that particular pixel, that is a value in a matrix. So you can think of your screen as a matrix that has values. So you have the location, okay, this will be, say, the first pixel over here. And then I will have some kind of value that tells me the color of my pixel. So I can think of matrices, and that's exactly how images are represented with matrices, where each entry in the matrix is a particular pixel, represents a particular pixel. When the singular value is large, that rank 1 matrix records very important features about the image. The smaller the the singular value, because remember, these are all positive numbers, the smaller the singular value, the less important the information that matrix brings. So normally, if you apply software to find the singular value decomposition of a matrix, you will get the sigma values in descending order. Sigma 1 will be bigger than or equal to sigma 2 will be bigger than or equal to sigma r. And we can talk about approximating matrices or say, how do you reduce the resolution? You could kill certain matrices which will with smaller singular values. And what that does is it maybe kills some very fine features of your image. But the big features that tell you like what's in the image are going to be stored in those matrices that have bigger singular values. So this is one way to do signal processing or image processing using the singular value decomposition. I know there is a lot of theory in this, and there is a lot more to be said about singular values and the singular value decomposition. But going forward, I want us to focus on finding the singular value decomposition. I will do that in the next video.